Section 9.3 is geometric sequences. I can define, identify, and apply geometric sequences. Big ideas here are, in a geometric sequence, the ratio of any term after the first to its preceding term is a constant value, no matter what two terms are compared. A geometric sequence can be built by multiplying each term by that constant. A geometric sequence can be modeled explicitly or recursively. So geometric sequences are very similar to the arithmetic sequences from last section. In arithmetic sequences, we add. In geometric sequences, we're going to multiply. Take note on page 580, talks about geometric sequences. Here it says, a geometric sequence with the starting value a and common ratio r is a sequence of the form a times r squared because we took times r again, ar cubed because we took a times r times r times r. Okay. Again, the difference here is that we have a common ratio because we're multiplying instead of a common difference in the arithmetic where we added. A recursive definition for the sequence has two parts again. So just like with arithmetic sequences, in a recursive formula, we tell what our first number is, and then we have a sub n equals a sub n minus 1. Instead of adding d, we multiply by r. So again, we have our first value, a sub 1, and our common ratio times our a sub n minus 1 in recursive. An explicit definition for this sequence is a single formula. A sub n equals a sub 1 times r raised to the n minus 1 power. Okay, when we're multiplying repeatedly, we use exponents. So the things that stay the same for our explicit formula here, every single time we put our a sub n and our n minus 1. The things that change are first term and our common ratio. Example 1, identifying geometric sequences. Is the sequence geometric? If it is, what are a sub 1 and r? So what are our first term and our common ratio? So here we're going to be looking to see if it's geometric. We're going to look and see if we can multiply by the same number every time. 3 to 6 is times 2. 6 to 12 is times 2. 12 to 24 is times 2. 24 to 48 is times 2. So every time we multiply by the same number, which means, is it geometric? Yes. A sub 1 is going to be our first value. And r is our common ratio. It's the amount that we multiply by every time. And here it's going to be 2. B, 3 to 6 is times 2. 6 to 9 is times 3 over 2. If you're not sure, take 9 divided by 6. Just like with our arithmetic sequences, we could take our second term minus our first term. Here we can take our second term divided by our first term, 3 over 2. 12 divided by 9, 4 over 3. 15 divided by 12, 5 over 4. Okay, so here we multiplied by 4/3. Here we multiplied by 5/4. Since those are not the same, it is not geometric. So we don't list a first term and we have no common ratio. Okay, here's a little bit trickier to tell. To go from 3 to the 5th power to 3 to the 10th power, we multiplied by 3 to the 5th power. Remember, when we multiply powers with the same base, we add our exponents. When we divide, we subtract. So I keep my base exactly as it is. I take 10 minus 5 and get 3 to the 5th power. 15 over 3 to the 10th. Same idea, I keep my base and I subtract my exponents, 3 to the 5th power. 3 to the 20th divided by 3 to the 15th. Keep my base, subtract my exponents, I get 3 to the 5th. So each time I multiplied by 3 to the 5th power, which means it is geometric. My first term is 3 to the 5th power, which is also my common ratio. My first term is here. My r is here. So they happen to be the same here, but make sure you know which one comes from where. Here again, we're determining if it's geometric. If it is, what's a sub 1 and r. So, since we're looking for geometric, we're looking for multiplication. 2 to 4 is times 2. 4 to 8 is times 2. 8 to 16 is times 2. So this is geometric. A sub 1 is where we start, and our r is what we multiply by every time. Here again, they both happen to be 2. B, to go from 1 to 5, I times by 5. 9 to 5, I can't multiply by 5. So I know that these are not equal. It's not geometric. If I look here, I add 4 every time, which means that that would be an arithmetic sequence like in 9-2. We'd have a common difference. Okay, here I'm going to multiply by 2. 3 to 7 is 4 times 2. 7 to 11 means I multiplied by 2 to the 4th power. I kept my base. I add exponents, so 11 plus 4 gets me to 15. Again, I could have also divided there and subtracted exponents to figure out my 4s. Since those are all the same, it is geometric. My first term is 2 cubed. My common ratio every single time is the same, and it's 2 to the 4th power. If you wanted to, you could put 8 and 16, but since all the rest of those are left in 2s, with base 2s, that's how I kept it. Analyzing geometric sequences here. What are the indicated terms of the geometric sequence? We want the 10th term of this sequence here. So, regardless of how we solve this, we're going to have to find our common ratio, figure out what's happening every time. So, 4 to 12 is times 3. 12 to 36 is times 3. So, our r value is going to be 3. And it told us it's geometric, so they aren't going to do anything fancy along the way and change that. Every time it's going to be times 3. So we can keep going in this pattern and keep multiplying by 3 and multiplying by 3 and multiplying by 3, but that seems like a lot. I know we're only finding the 10th term, but still. Instead, what I'm going to do is I'm going to come up with the explicit formula. With the explicit formula, again, we have exactly one equation. We can find the exact value we're looking for. In recursive, we have to repeatedly multiply. So, our framework here is a sub n equals a sub 1 times r, our common ratio, and how many times we multiply is an exponent, and minus 1. We represent repeated multiplication with exponents. We plug in some values here because we know a sub 1 is 4, and our common ratio is 3. And this right here is our explicit formula. Exactly 1. We want the 10th term, so I'm going to plug 10 in for n. Here, 4 times 3 to the 9th power. Okay, we can plug it in to our calculator and get 78,732. And that is the value of the 10th term in our sequence. Second and third terms here. Remember, every time we move from one term to the next in a geometric sequence, we multiply by r. So I multiply by r here, and here, and here. So I've taken 2 and I've multiplied by r 3 times and gotten negative 54. So I can set up an equation to figure out what r is. I took 2 times r times r times r, and I got negative 54. I can rewrite this right here as r cubed. Again, we use repeated multiplication, exponents for repeated multiplication. Divide by 2 to get r by itself. And to get rid of a cubed, we take the cubed root. And r is going to be negative 3. Now that I have that, in order to find my values, I can take where I started times my r to get my next value. I'm going to use the recursive formula here. I take my previous term times my r value and get my next term. I'm going to do it one more time just to double check and make sure I get to where I need to be with negative 54, and I do. So negative 6 and 18. Second term of the geometric sequence here. Geometric means I multiply, and I multiply. So I have 3, I multiplied by r, and I multiplied by r, and I got to 12. I can rewrite this r times r as r squared, and I have 3r squared equals 12. Divide by 3, r squared equals 4. Take the square root of both sides, and whenever we take the square root, we get plus or minus 2, which means right now I have 2 options. R could have been 2, or r could have been negative 2. So I have to check both of those, and I'll get 2 different options for my second term. I take my first term, multiply by my r value, and I get 6. Take 6 times 2 and get 12. That would work. My other option would have been if I took 3 times negative 2, if my r was negative 2. I'd get negative 6. Negative 6 times negative 2. My previous term times my r value gets me to 12. So the second term in my sequence is either 6 or negative 6. So when I write that, my sequence would have been 3, 6, 12, and remember dot, dot, dot just means it continues, or 3, negative 6, 12, and continued on. I'm going to do this one on the next